What if one of the greatest physicists of the 20th century looked at the most successful theory of matter ever created and simply refused to believe it? Richard Feynman, the man who gave us Feynman diagrams, who revolutionized quantum electrodynamics, who won the Nobel Prize for making the impossible calculable. This same Richard Feynman stood in front of his colleagues and said, "No, not to bad science, not to pseudoscience, but to quarks, the very building blocks of protons and neutrons that every physics textbook now treats as gospel." Why would a genius reject genius? The answer reveals something profound about how science actually works, about the tension between mathematical beauty and physical reality, and about a rivalry so intense it shaped modern particle physics. Let me take you inside one of the most fascinating scientific controversies of the 20th century. To understand why Feynman refused quarks, we need to go back to a time when physicists were drowning. Not in water, but in particles. Imagine you are a physicist in the 1950s. You think you understand matter. Atoms are made of protons, neutrons, and electrons. Simple, elegant, nice, done. Then the particle accelerators turn on, and suddenly particles start appearing everywhere. The muon, the pion, the kaon. Strange particles that behaved in ways nobody expected. By the early 60s, there were so many new particles that physicists started calling it the particle zoo. Hundreds of supposedly fundamental particles, each with different masses, charges, and behaviors. Something was clearly wrong. Nature does not build zoos. Nature builds elegant systems. Enter Murray Gell-Mann. A theoretical physicist at Caltech with an encyclopedic mind and an ego to match. Gell-Mann looked at this chaos and saw hidden order. He developed something called the Eightfold Way, a mathematical pattern that organized all these particles into families, just like Mendeleev had organized elements into the periodic table. But Gell-Mann did not stop there. In 1964, he asked a radical question. What if protons and neutrons were not fundamental at all? What if they were made of something smaller? He proposed that all these hundreds of particles were actually combinations of just 3 types of truly fundamental particle. He needed a name for them. And here's where Feynman enters the story, though in a way most people never hear about. According to Feynman himself, he and Gell-Mann were talking one Friday about these hypothetical particles and needed something to call them. Feynman suggested they call them quarks. Just a placeholder. A joke, really. But Gell-Mann was not a man who took names lightly. Well, by Monday he had found the word quark in James Joyce's Finnegan's Wake. 3 quarks for muster mark. The name stuck. Feynman would later mock this obsession with names. Having a name for something does not tell you a damn thing, he would say. What matters is what it does. And this disagreement about what matters would become central to everything that followed. Now, you might think Feynman rejected quarks because he was jealous of Gell-Mann's idea. The 2 men were rivals after all. They worked in offices near each other at Caltech, competed for attention, and argued constantly. But Feynman was not petty about physics. He had legitimate scientific objections. Here was the problem. Gell-Mann himself called quarks mathematical entities in his first paper. He was not entirely sure they were real particles, and there were good reasons for doubt. First, quarks would have to carry fractional electric charge, 2/3 or 1/3 of an electron's charge. Nothing in nature had ever been observed with fractional charge. Everything came in whole units. This was like proposing that some coins are worth half a cent. The currency of nature did not seem to work that way. Second, and more troubling, nobody had ever seen a free quark. Not one. Ever. If protons were made of quarks, why could we not smash a proton hard enough to knock a quark loose? Every time physicists tried, they just got more particles. More combinations. Never a naked quark wandering alone. Gell-Mann had to propose that quarks were somehow permanently confined inside larger particles. They existed, but could never be observed directly. Stop. Bati. Think about that for a moment. A particle that is real but can never be seen. A building block that can never be isolated. This sounded to many physicists like cheating, like inventing invisible elephants to explain the footprints. Feynman was deeply suspicious of theories that could not be tested. He had built his entire approach to physics on connecting mathematics to measurable reality. His famous Feynman diagrams were not just pretty pictures. They were calculational tools tied directly to experimental predictions. So when Gell-Mann talked about quarks that could never be observed, Feynman heard something that sounded disturbingly like philosophy, not physics. But Feynman was not just a critic. He was a builder. And in 1968, he built something remarkable. He was visiting SLAC, the Stanford Linear Accelerator Center, where physicists were doing a new kind of experiment. They were firing electrons at protons at enormous energies and watching how the electrons scattered. It was like throwing tiny bullets at a target and seeing what angles they bounced off at. The results were strange. The electrons were scattering, as if they were hitting something small and hard inside the proton. Something point-like. The SLAC theorist James Bjorken had already noticed a peculiar pattern in the data, something called scaling. The way electrons scattered depended on a specific combination of energy and momentum, not on each variable separate. This was a fingerprint of internal structure. Feynman saw these results and became electrified. Overnight, he wrote down a set of equations that would change particle physics. He called his idea the parton model. The name parton was deliberately vague. Part of a proton, part of a neutron. Feynman did not want to commit to what these parts actually were. He only wanted to describe what they did. In Feynman's model, when you looked at a proton moving at nearly the speed of light, you saw it as a collection of point-like particles, each carrying some fraction of the proton's momentum. The electrons scattered off these partons like billiard balls clicking against each other. Clean. Simple. Nice. Calculable. This was pure Feynman. No metaphysical claims about ultimate reality. No invisible entities that could never be detected. Just a description of what experiments actually measured. Gell-Mann was furious. He called partons protons, a pun and an insult. To Gell-Mann, Feynman was being willfully obtuse. The partons were obviously quarks. Why pretend otherwise? But Feynman had a response, and it revealed the deep philosophical divide between them. Imagine you have a black box. You can put things into it and measure what comes out, but you cannot open. You run 1,000 experiments and develop a model that perfectly predicts every output from every input. Now someone tells you they know what is inside the box. Little green gears and purple springs, they say. And their theory also predicts the outputs correctly. Are the green gears real? How would you know? This was essentially Feynman's position. The parton model worked. It made predictions. Those predictions matched experiments. Why add extra assumptions about what partons really were? Gell-Mann saw it differently. Nice. To him, the quark model was not just a calculational convenience. It was a glimpse into deeper reality. Quarks had properties. They came in types he called flavors. Up quarks and down quarks and strange quarks. They had specific charges and masses. The mathematics required it. But here is where it gets interesting. For years, the two models coexisted, each with its advocates. Physicists talked about the quark parton model, hedging their bets. The parton model was easier to calculate with in certain situations. In 1971, the quark model explained why particles came in the families they did, and Feynman kept resisting the full quark picture. He had, according to Gell-Mann, some other cuckoo scheme based on his part. He was very bright, Gell-Mann recalled, and realized after a while that we were correct, but he resisted it. Why did Feynman resist? This is the crucial question. Feynman's hesitation was not stubbornness. It was philosophy dressed as physics. Throughout his career, Feynman had been burned by the gap between mathematical elegance and physical reality. He had spent years trying to eliminate infinities from quantum electrodynamics, those maddening divergences that appeared in calculations. His solution, renormalization, worked brilliantly in practice. The predictions matched experiments to extraordinary precision. Wow. But Feynman himself called it a dippy process. Hocus pocus. He suspected that renormalization was not mathematically legitimate, even though it were. He had learned, painfully, that beautiful mathematics does not guarantee physical truth. A theory could calculate everything correctly, and still be fundamentally wrong about what reality actually is. So when Gell-Mann presented quarks as the true constituents of matter, Feynman wanted more than mathematical consistency. He wanted direct evidence. He wanted to see a quark or measure one, or find some way to test whether quarks were real particles or merely useful fiction. The parton model gave him a way to stay agnostic. To say, we can describe the experiments without committing to the metaphysics. It was a profoundly cautious position, and in the end, it was probably too cautious. By the mid-1970s, the evidence for quarks became overwhelming. Not because anyone found a free quark, but because the theory that included quarks, called quantum chromodynamics or QCD, made predictions that nothing else could match. QCD explained why quarks had to be confined. The force between quarks actually gets stronger as they move apart, like a rubber band that stiffens as you stretch it. Try to pull a quark out of a proton, and the energy you put in creates new quarks instead. You can never isolate one. The confinement was not a bug, but a feature of the theory itself. QCD also explained the deep inelastic scattering results that had inspired the parton model. Partons were quarks, plus gluons, the particles that carry the strong force between quarks. Everything fit together. Feynman, being a great physicist, recognized when the evidence turned against him. When the fifth quark was discovered, he immediately told his students that it implied a sixth quark must exist. He was right. The sixth quark was found after his death. He did not cling to his parton model out of pride. He adapted, but he had fought for something important, even in losing. Here is what most accounts of this story miss. Feynman was not wrong to be skeptical. He was applying exactly the kind of rigorous doubt that science requires. Every new theory should face that scrutiny. Right. Every claim about ultimate reality should be questioned. Gell-Mann was not wrong to push for deeper structure. Science progresses by proposing bold theories and testing them against evidence. If everyone waited for certainty, we would still be stuck at the beginning. The controversy between them was not dysfunction. It was science working exactly as it should. Two brilliant minds with different philosophical instincts, pushing against each other until nature revealed which path led closer to truth. And there is a deeper lesson still. The parton model and the quark model turned out to describe the same reality from different angles. Partons were how quarks looked in high-energy collisions, when their interactions became simple and almost free. Quarks were the full picture, including their complex behavior at lower energies. Neither was wrong. They were both partial views of something more complete. This happens again and again in physics. Wave or particle. Both. Position or momentum. Complementary. Different descriptions, each capturing something true, none capturing everything. Feynman knew this pattern well. He had helped create the path integral formulation of quantum mechanics, a third way of looking at quantum theory that was mathematically equivalent to wave mechanics and matrix mechanics, but revealed different insights. Maybe his resistance to quarks was partly this instinct. A sense that the parton description captured something the quark description missed. Something about what we can actually measure, what experiments actually tell us. Feynman once said that the beauty of a flower is not diminished by scientific understanding. Knowing the cells and the chemistry only adds to the wonder. The science is additional beauty. The same applies here. Knowing that protons are made of quarks, that quarks are bound by gluons, that the strong force has this strange property of growing with distance. This knowledge does not diminish the mystery. It deepens it. Why does nature build matter this way? Why these rules and not others? Why does mathematics describe reality at all? Feynman never stopped asking these questions. Even when he accepted quarks, he never stopped poking at the foundations, never stopped wondering if the current story was the final story. It almost certainly is not. Quantum chromodynamics is spectacularly successful, but it does not explain everything. It does not tell us why there are 3 generations of quarks, or why their masses have the values they do, or how gravity fits into the picture. The next Feynman, the next Gell-Mann, might be working on these questions right now, and they will probably argue with each other just as fiercely. That's not a failure of science. That is science at its best. Richard Feynman refused to believe in quarks not because he was foolish, but because he took the question of reality seriously. He wanted to know not just whether a theory worked, but what it meant for the theory to work. Whether calculating correct answers was the same as understanding nature. These are questions that every physicist struggles with. They are questions that do not have easy answers. When Feynman finally accepted the quark model, he did not admit defeat. He recognized that the evidence had spoken. Nature had cast its vote, and in science, nature always wins. But the struggle mattered. The doubt mattered. The insistence on proof over elegance, on observation over assumption. These are the muscles that keep science honest. The next time you hear about quarks, about the particles inside the atoms, inside everything you see and touch, remember that even Richard Feynman hesitated to believe. Not because he lacked imagination, but because he had too much respect for the difficulty of knowing what is real. And that hesitation, that beautiful stubbornness, is exactly what we need more of in a world eager for easy certainties. The universe does not care about our comfort. It rewards only those who keep asking, keep doubting, keep looking. That is the lesson Feynman taught. Not just in his successes, but in his refusals. Keep questioning. Keep wondering. The best answers are always waiting on the other side of the hardest doubts. Final visual. Channel closing.